What if I told you that the universe is not chaos, it's a game, a silent, invisible game being played across an infinite board? The waves crashing against the rocks, the planets circling distant stars, the atoms inside your body vibrating right now, all of it following rules. Rules so precise that we can predict eclipses centuries in advance. Rules so elegant that they fit into a single line of algebra. But here's the part that should make you uncomfortable. Those rules are written in mathematics. And mathematics is something we invented. We made up the symbols, we defined the numbers. We imagined the square root of -1. So why does the universe obey it? Why does something we created inside our minds describe something that existed billions of years before we were born? Is math the language of reality, or is reality mathematical at its core? That is the mystery. You can never unsee it. The world is a wild place, complicated, noisy, restless. Look around and you see waves crashing against rocks, clouds forming and dissolving overhead, trees bending in the wind. Everything moves, everything shifts. It feels messy, a blur of color, motion, and sound. And yet beneath that chaos, we carry a strange intuition, a quiet belief that under all this confusion, there are rules, that something structured is happening underneath the surface, that this is not random noise, it is a game. Imagine for a moment that the universe is like an enormous chessboard, infinite in size. The edges are beyond sight. The pieces are so small we can barely make them out. And we as observers are not players. We are the audience. We sit and watch. A piece moves. We lean forward. We try to guess the rules. If this piece moves here, what happens next? If that pattern repeats, what does it mean? That process, the careful watching, the guessing, the writing down of patterns, is what we call physics. It is humanity's attempt to reverse engineer the rules of the cosmic game by observing the moves. But here's the unsettling part. The rules we discover, the equations we carefully write in notebooks, are expressed in mathematics. And mathematics is something we created. We decided that 1 + 1 = 2. We defined triangles. We invented calculus to describe change. These are constructs of the human mind, just like chess itself. So here's the mystery. Why does the universe obey mathematics? The universe does not care about us. It does not care about us. It does not care about our symbols, our textbooks, or our blackboards. And yet, when we write the right equation, when we scribble the correct symbols on a napkin, we can predict where a planet will be 1,000 years from now. We can calculate how a bridge will hold weight. We can describe how an atom behaves. It is as if the universe speaks mathematics, but that cannot be the whole story. We invented math. We did not invent the universe. So how can something we created align so perfectly with something that existed long before us? There is a deep connection here, a connection between the logic of our minds and the structure of reality, and we do not fully understand it. To see how strange this is, let's go back in time. The Babylonians were extraordinary sky watchers. They tracked the moon, the sun, and the planets with impressive accuracy. They built tables that predicted eclipses. They saw patterns and used numbers to forecast celestial events. But they did not know the Earth orbited the sun. They did not use geometry the way the Greeks later would. They calculated, but they did not explain. Then came the Greeks. The Greeks loved logic. They loved certainty. They began with simple statements, axioms. A straight line is the shortest distance between 2 points. Parallel lines never meet. From these starting points, they built entire systems of reasoning. They proved theorems using nothing but thought. They closed their eyes and constructed a towering structure of geometry purely from logic. They were not looking outward at the world. They were looking inward at the consistency of ideas. Fast forward to Isaac Newton. Newton asked a question no one had dared to connect before. Is the force that pulls an apple to the ground the same force that keeps the moon in orbit? At first glance, those motions look completely different. The apple falls straight down. The moon circles endlessly. One crashes. The other glides. But Newton suspected a single underlying rule. Using geometry inherited from the Greeks and inventing a new mathematical tool, calculus, he found something astonishing. If gravity weakens with distance according to an inverse square law, then the motion of the moon and the fall of the apple are governed by the same principle. An inverse square law means this: if you double the distance, the force becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. The force spreads out as the square of the distance. Think of a light bulb. As light radiates outward, it spreads across larger and larger spheres. The surface area of a sphere increases with the square of the radius. So the brightness fades with distance squared. Gravity behaves the same way. Newton wrote it down simply. Force equals a constant times one mass times another mass divided by the distance squared. A single line of algebra. Yet that one equation means every object in the universe attracts every other object. You are pulling on the moon right now. The moon is pulling on you. A distant galaxy is tugging on your body ever so slightly, and the math works perfectly. We use it to predict tides, to launch spacecraft, to weigh planets, to navigate probes across billions of miles. But pause for a moment and ask, why is the rule so simple? Why does gravity depend only on mass and distance? Why not color? Why not temperature? Why not the day of the week? The laws of physics have an elegance, a simplicity that mathematics captures beautifully. But here is the trap. The math is not the thing itself. It is a description. You could rewrite Newton's theory and say invisible angels push planets toward the sun. As long as the angels push with a force proportional to 1 over distance squared, the predictions would be identical. The math would not change. The difference is that angels add unnecessary baggage. So we apply Occam's razor. We remove what we cannot observe. We keep only what is needed. Mathematics becomes the scoreboard, not the game. And yet it keeps working again and again, which brings us back to the unsettling question. Did we invent mathematics or did we discover it? And why does it fit the universe so perfectly? That is the mystery. Newton's laws work beautifully. For centuries, they seemed complete. Planets moved exactly where the equations said they would. Comets returned on schedule. Tides rose and fell predictably. It looked as though we had decoded the rules of the cosmic chessboard. But there was a quiet discomfort hidden inside Newton's theory. Gravity, according to Newton, acted instantly across space. The sun somehow knew where the Earth was. If the sun vanished, Newton's equations implied the Earth would immediately fly off into space. The force acted at a distance with no visible connection between objects. That felt strange, almost magical. Then came Albert Einstein, and he changed the picture entirely. Einstein began with a radical idea. Nothing can travel faster than light. Not matter, not energy, not even information. If that is true, then gravity cannot act instantaneously. Something about Newton's picture had to give. So Einstein reimagined the stage on which the universe plays its game. Instead of space and time being an empty box where things happen, he proposed that space and time are woven together into a fabric. Space-time, this fabric, is flexible. It bends, it curves. Mass and energy do not pull on objects through invisible strings. Instead, they deform the geometry of space-time itself. Picture a stretched rubber sheet. Place a heavy bowling ball in the center. The sheet dips. Now roll a marble across the surface. The marble curves toward the bowling ball, not because the bowling ball is pulling it with a string, but because the surface it travels on is curved. That is gravity in Einstein's universe. The Earth orbits the sun, not because it is being pulled by a force in the Newtonian sense, but because it is moving along the curved geometry created by the sun's mass. It is following the straightest possible path, but the space it moves through is not straight. An ant walking across a curved apple thinks it is walking in a straight line. From its perspective, everything feels flat, but from the outside we see the curvature. Einstein's insight was that we are the ant. This was not just philosophy. The math predicted new effects. Light would bend around massive objects. Time itself would slow down in strong gravitational fields. Clocks on fast-moving spacecraft, T would tick more slowly than clocks on Earth, and the experiments confirmed it. GPS satellites must account for Einstein's equations. Without corrections from relativity, your phone's navigation would drift miles off course within hours. The curvature of space-time is not poetic metaphor, it is measurable reality. But here is the astonishing part. To describe curved space-time, Einstein needed advanced mathematics, differential geometry. The tools he used had been developed decades earlier by mathematicians exploring purely abstract ideas. They were asking what would happen if parallel lines could meet. They were not thinking about gravity. They were playing with logical possibilities. Yet those abstract structures turned out to be exactly what was needed to describe the real universe. How did mathematics developed in isolation from experiment end up being the perfect language for gravity? Were those mathematicians discovering something fundamental about reality without realizing it, or were they inventing tools that just happened to fit later? The mystery deepened, and then came quantum mechanics. If relativity reshaped our understanding of the very large, quantum theory shattered our intuition about the very small. At atomic scales, particles do not behave like tiny billiard balls. They do not even behave purely like waves. They behave like something stranger, something we describe using probability amplitudes. Here is one way to picture it. Imagine a photon of light traveling from a lamp to a mirror and then into your eye. Common sense says it takes the straight line path, the shortest distance, the fastest route. But quantum mechanics says something astonishing. The photon takes every possible path. It goes left, it goes right, it loops wildly, it wanders in impossible spirals. It even takes paths that swing out to distant galaxies and back. Every conceivable route contributes. For each path, we assign a tiny arrow, a probability amplitude. The length of the arrow relates to likelihood. The direction of the arrow depends on how long the journey took. Now comes the strange part. To determine what actually happens, we add up all these arrows. We place them head to tail in sequence. For the wildly different erratic paths, the arrows point in many directions, up, down, left, right. When you add them together, they cancel out, they interfere destructively, their contributions sum to nearly zero. But for paths very close to the straight line path, paths with nearly identical travel times, the arrows align. They point in almost the same direction. When added together, they reinforce one another. The result is a large arrow. That is why light appears to travel in straight lines. Not because it only chooses the straight path, but because all the other paths cancel themselves out. Nature is not lazy. It is not selecting the shortest route. It is exploring all possibilities simultaneously, and the mathematics of interference determines what survives. This principle is called the principle of least action, but it is more subtle than the name suggests. It is not that nature prefers efficiency, it is that the mathematics of complex amplitudes makes certain outcomes overwhelmingly dominant. And to describe these amplitudes, we must use complex numbers, numbers involving the square root of -1. Pause and consider that. There is no real number which, when multiplied by itself, equals -1. We invented an imaginary number denoted by I to solve algebraic equations that otherwise had no solutions. At first, imaginaire, Y numbers seemed like a mathematical trick, a convenient fiction. Yet quantum mechanics cannot function without them. The arrows representing probability amplitudes are complex numbers. Their directions depend on phases involving I. Remove imaginary numbers, and the theory collapses. The universe, it seems, runs on mathematics we once considered imaginary. Electrons orbit nuclei according to equations involving complex exponentials. Chemical bonds depend on them. The stability of atoms depends on them. Without imaginary numbers, there would be no chemistry, no biology, no life. How can something imaginary describe reality so precisely? Again, we face the unsettling question: are we inventing mathematics or uncovering something woven into the fabric of existence? And quantum mechanics brings yet another puzzle. When physicists calculate certain quantities, like the energy of an electron interacting with its own electron magnet, its own electromagnetic field, the math sometimes produces infinity. Not a very large number, infinity. An electron cannot contain infinite energy. So physicists developed a technique called renormalization. In simple terms, it involves subtracting one infinity from another in a carefully controlled way, leaving behind a finite, measurable result, like sleight of hand, like sweeping dust under the rug. And yet, after performing this mathematical maneuver, the predictions match experiments with extraordinary precision. The agreement between theory and measurement in quantum electrodynamics is accurate to many decimal places, equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. We use imaginary numbers. We manipulate infinities. We perform mathematical tricks, and reality agrees. Why? It is as though mathematics is not just a language we invented, but a flashlight illuminating something deeper. We may not see the ultimate substance of reality, but we see patterns, we see relationships. Relativity reveals curved space-time. Quantum mechanics reveals interference of probability amplitudes. Both rely on abstract mathematics developed by human minds, and both describe nature with astonishing accuracy. We are left with a profound tension. But does it explain what reality is, or does it only describe how it behaves? The deeper we go, the stranger it becomes, and the game continues. At this point, we have to slow down because there is a danger hidden in all this success. Mathematics works. It works astonishingly well. It predicts planets, bends light, explains atoms, and powers the devices in your pocket. But we must not confuse the map with the territory. The equations are not reality itself. They are representations, symbolic compressions of patterns we observe. Imagine holding a map of a city. On the map, roads are thin black lines, rivers are blue curves, parks are green patches. If you follow the lines correctly, you will reach your destination. The map works, but the lines are not roads. The ink is not asphalt. The symbols are not the city. Mathematics is our map of the universe. And sometimes we forget that. Take modern quantum field theory. When we push our equations far enough, when we try to calculate certain interactions at extremely small scales, infinities appear again. We patch them. We renormalize them. We adjust parameters so that our predictions align with experiment, and it works, but it feels incomplete, like we are tuning an instrument without fully understanding how it was luti. It is as if we know the score of the music, but we do not know what the instruments are made of. Here is another way to picture it. Imagine a sausage. Slice it straight down, you get a circle. Slice it at an angle, you get an oval. Slice it lengthwise, you get a long strip. The sausage is reality. The slices are our perspectives. In relativity, space and time are not separate ingredients. Space and time are not separate ingredients. They are fused into a four-dimensional block. Space-time, past, present, and future all exist within this block, like the meat inside the sausage. When we move through time, we are not moving along a universal clock. We are slicing through space-time at a particular angle. Move slowly, and your slice looks one way. Move close to the speed of light, and your slice tilts. Time slows down. Length contracts. The geometry of your slice changes. The Lorentz transformations, the equations of special relativity, tell us exactly how the slice rotates depending on speed. The math is flawless, but does it tell us what the sausage is made of? No. It tells us the structure of the slices. It tells us how measurements change. It tells us relationships between observers, but it does not reveal the underlying substance. We know the rules of the chess game, at least some of them, but we do not know why the game is being played. We do not know what the board is made of. We do not know if there is a final move. And perhaps that is okay. There is a temptation in science to search for the ultimate equation, the final formula you could print on a t-shirt, the single line that explains everything: gravity, quantum mechanics, dark matter, consciousness, the theory of everything. Maybe we will find it. Or maybe reality is layered like an onion. We peeled back one layer with Newton. Underneath we faux, and Einstein. Beneath quantum mechanics. Each layer revealed deeper structure and deeper mystery. Perhaps there is another layer below the quantum one. Perhaps electrons are not fundamental. Perhaps space-time itself is emergent from something even more abstract. Information, geometry, computation, or perhaps there is no bottom at all. Maybe the onion has infinite layers. What we do know is this: mathematics has been our most reliable flashlight in the dark. It is a tool forged entirely in the human mind. Symbols, logical rules, abstractions, and yet it unlocks the behavior of stars and galaxies. It explains the rainbow in the sky and the atoms in your body. When you see a rainbow, you can admire the colors. You can call it poetry in the sky. But a physicist sees angles of refraction, wavelengths, droplets acting as tiny prisms. He sees geometry written in light. Does that make the rainbow less beautiful? No. It makes it more beautiful because now you see two layers at once: the color and the cause, the sensation and the structure, the poetry and the math. The same equations that bend light into a rainbow also govern nuclear fusion inside stars. They also govern the electromagnetic forces holding your molecules together. You are not separate from the mathematical structure of the universe. Every thought you have, every memory, every emotion, all of it arises from atoms following quantum rules and fields, obeying relativistic geometry. And yet, here you are. The universe has produced a configuration of matter capable of asking questions about itself. That may be the strangest fact of all. We are not outside observers of the cosmic game. We are pieces on the board that have become conscious of the board. We can step back, at least intellectually, and ask why the rules are what they are. Why inverse square laws? Why complex numbers? Why curved space-time? Why something instead of nothing? We may never answer the ultimate why. Science is extraordinarily powerful at explaining how. It reveals mechanisms, patterns, symmetries, but the deeper reason, if there is one, may lie beyond our reach. And that is not a failure, it is an invitation. Because if we knew everything, if every mystery were solved, the game would end. The exploration would stop, the chase would be over. The thrill of science is not certainty, it is discovery. The moment when a new equation suddenly makes sense of scattered clues. The moment when an experiment confirms a daring prediction. The moment when a deeper symmetry is uncovered beneath apparent chaos. Those are victories of the human mind. We are small creatures on a small planet orbiting an ordinary star in an unremarkable galaxy. We can detect gravitational waves from colliding black holes billions of light years away. We can manipulate quantum particles in laboratories. We built these tools from thought alone. So do not fear mathematics. Do not reduce it to classroom drills and homework assignments. It is the secret language of nature. It is the music beneath the motion. Even if we invented the notes, the melody is real. The melody is playing in the silence of space, in the vibration of fields, in the curvature of space-time, in the interference of quantum amplitudes. Our task is to listen carefully, to keep asking questions. Why does it wiggle like that? Why does it fall like that? Why does it curve, interfere, resonate? And when you find an answer, ask again, because every answer opens another door, every laugh you peeled reveals another beneath it. The universe is stranger than our intuition, deeper than our imagination, and more mathematical than we ever expected. Yet it remains mysterious, and that is exactly how it should be, because the moment the mystery disappears, the game ends. And for now, the game is still on.